We've seen how incredible large language models are, storing so much knowledge in their parameters. It feels like they know everything, right?
They definitely have an impressive ability to store factual knowledge, as this 2020 paper points out. But that knowledge is fixed at training time, presenting some real challenges.
Limited? But they can answer so many questions. What kind of limitations are we talking about here?
The paper identifies a key issue. While they store knowledge, their ability to precisely manipulate it, especially for complex or very specific knowledge-intensive tasks, is constrained. This leads to common problems.
So, a model trained 2 years ago won't know about current events. How do we keep these vast models up to date without constantly retraining them?
Exactly. Updating their world knowledge is a huge and expensive problem. Retraining is infeasible for every new piece of information.
Imagine a student who has learned a lot, but can also instantly look up specific facts in a textbook. RAG aims to give our LLM that textbook lookup ability, using what's called non-parametric memory. However, unlike a human student, the LLM doesn't truly understand or deeply reason with the facts it finds. It uses them as richer input for its pattern-matching text generation capabilities.
Like giving the model a brain and a library, so it doesn't have to remember everything, it just needs to know how to find it.
That's exactly the core idea this paper introduces: retrieval-augmented generation. It defines RAG as models which combine pre-trained parametric and non-parametric memory for language generation.
Parametric memory is the knowledge learned in training, right? And non-parametric is the external library data?
Precisely. In their original formulation, the parametric memory is a pre-trained seek-to-seek model, likely a transformer, which we've discussed before. The non-parametric memory is a dense vector index of Wikipedia.
So it's not just retrieving text, but using a vector index. That implies some kind of embedding and similarity search we've seen in other contexts.
Yes, the vector index is accessed with a pre-trained neural retriever. This retriever learns how to find relevant information from the external knowledge base given a query.
This connects to our episode on transformers, TCM 003002. The idea of encoding information into vectors for efficient lookup seems very similar.
Crucially, the original RAG paper introduced a differentiable access mechanism to this non-parametric memory. This means the retrieval step itself is part of an end-to-end trainable model, allowing gradients to flow back and improve both the retriever and the generator jointly.
So it's not just two separate pieces bolted together, but they actually learn to work better with each other over time, refining how the LLM asks for and uses information.
The immediate impact was significant. The original RAG paper reported setting the state of the art on 3 open domain QA tasks, including prominent benchmarks like web questions and natural questions, often showing significant improvements over parametric-only models.
That's impressive. It shows this isn't just a theoretical idea, but a practical improvement for answering questions.
This foundational paper laid the groundwork. Now, let's explore why RAG became such a critical solution for overcoming persistent LLM limitations, even beyond factual accuracy.
I'm curious how it handles issues like models just making things up.
So we mentioned LLMs making things up. What's the technical term for that, and why does it happen?
That behavior is known as hallucination. It's when models confidently produce inaccurate or irrelevant output. It's a major limitation for trustworthiness.
It's not just being wrong, it's being confidently wrong. That feels more dangerous.
Absolutely.
This leads to confidently inaccurate and irrelevant output, eroding user trust. RAG directly addresses this by providing external grounding. One key reason for hallucinations is the knowledge cutoff. After a model is trained, its data is frozen. This creates a knowledge gap for recent events.
So, asking about a specific news event from last week would likely result in an imaginative but incorrect answer if the model hasn't been updated.
Think of it this way. The LLM is like a brilliant orator who only knows what they've memorized. RAG is like giving them an instant research assistant to consult authoritative, external data before they speak. This analogy holds well for the LLM using the retrieved facts to inform its output, but it breaks because the research assistant, the retrieval system, isn't sentient or capable of interpreting the research itself. It simply provides raw text for the LLM to process.
So the LLM isn't trying to recall every fact itself. It's getting fresh, relevant context from this assistant to inform its answer.
Yes, the retrieved data and user query are combined into an augmented prompt. The model then generates output using this context to drive a more accurate and relevant response.
This means the LLM isn't just making things up from its internal memory. It's explicitly given information to work with.
One huge benefit is access to real-time data and proprietary or domain-specific data. This lets companies use LLMs on their internal documents, for instance.
That's critical for business. They need models that understand their unique information, not just general internet knowledge.
And this leads to building trust. More accurate and relevant results, often with source citations, allow human review, which is something base LLMs struggle with.
So not only is the answer better, but I can actually check where it came from. That's a huge step towards reliability.
Now that we have an intuition for why RAG is so valuable, let's look at the concrete steps, the mechanism of how it actually works to deliver these benefits.
I want to see how this research assistant actually finds and provides that relevant context.
A common conceptualization breaks RAG down into 4 core components: ingestion, retrieval, augmentation, and generation. Let's walk through them.
4 distinct stages, so it's a pipeline, not just a single model interaction?
Exactly. First is ingestion. Your authoritative data, be it private documents or a fresh news feed, is loaded into a data source, commonly a vector database.
This is where our library or textbook gets created and organized then.
During ingestion, you first chunk the data. You break your large documents into smaller, manageable pieces that are easier for the retriever to handle. The size and strategy for chunking are crucial. Too small, and you might lose important context or relationships between pieces of information. Too large, and you risk introducing irrelevant noise, exceeding the LLM's context window limits, or making the retrieval less precise.
So it's not just about breaking it up, but finding the right grain size for the information, like finding the right paragraph or section, not just random sentences, to ensure the LLM gets a complete thought.
Then you create vector embeddings for each chunk. An embedding model, which is a specialized LLM, converts each text chunk into a numerical vector.
This is where that transformer knowledge TCM-003002 comes in. We're representing text as dense vectors, capturing its meaning numerically.
These vector embeddings are then loaded into a vector database. This database is specifically designed for efficient similarity searches, even across very large collections of vectors.
So ingestion is essentially pre-processing all our external knowledge and getting it ready for speedy lookup.
Next comes retrieval. When a user asks a question, that query is also converted into a vector using the same embedding model. The system then performs a semantic search, finding the most semantically similar chunks in the vector database by comparing their embeddings, often using a measure like cosine similarity, and selects the top k most similar results.
It finds the chunks whose embeddings are most similar to the query embedding, right? That's semantic search in action.
The third step is augmentation. The most relevant chunks found during retrieval are then carefully inserted alongside the original user query into a predefined prompt template. This combined text forms a new enhanced prompt, often called an augmented prompt, for the LLM.
This is where the LLM gets its notes. It's not just the question, but also the answer-relevant context.
Finally, generation. The LLM receives this augmented prompt and generates its response. It uses the provided context, making its output more accurate, relevant, and grounded.
So the LLM is no longer guessing or hallucinating. It's specifically instructed to answer based on the retrieved information.
While RAG significantly improves grounding, it's not a silver bullet. The LLM can still misinterpret the retrieved context, ignore it entirely, or even hallucinate by fabricating details within the provided context if the prompt isn't carefully engineered. It also relies heavily on the quality and comprehensiveness of your external data, the effectiveness of the chunking strategy, and the accuracy of the retrieval system. So, garbage in, garbage out still applies, and the LLM itself still has its own quirks and limitations, even when given excellent contextual data.
One more thing that makes RAG so compelling. It's often more cost-effective compared to alternatives like repeatedly training or fine-tuning massive models. And it avoids the performance and cost pitfalls of stuffing too much raw data into a context window.
So it's not just better, it's often more economical than trying to make an LLM know everything internally.